Hello everyone. So I can see some of you are probably watching it, and so I got some of your queries. Last probably 3-4 queries I haven't answered. Actually, I actually gave the answers to my TAs. They will upload it. So I think some of you have some queries regarding some assignments, and maybe 2-3 questions. They maybe answers may be wrong, and somehow when it was printed, kind of like when I wrote the answers, it was correct, and then my TAs, when they typed it, couple of questions, a little bit discrepancies are there, and you don't need to worry about worry about that. So I think some of the questions probably like I can see one of the questions probably. So I think maybe question number 8 in assignment 1, that is one question. So you had some issues with that. Yeah, that's probably the answer is not correct. And question number 16 in assignment 3 also, yeah, assignment 3 probably some of you asked about that, but I did not get a question queries from you, that is regarding assignment number 3 and question number 17, that I did not understand properly. I posted all the answer from my side. So if you have some any doubts, you can again yeah, you can again probably reply in that, or we can ask fresh queries. So I got a question here: how to find the strain rate in bullet impact on a plate. Okay, so these things probably what we can do is we can probably wait about this. This is a very interesting question, and earlier also I told in the initial classes about how to find the strain rate. In the very beginning I told a very simple example, but please wait on that, because the next week, probably next to next week, we have the experimental techniques on dynamic deformation. There we have actually discussed 3 different cases of finding the strain rate. So probably we can discuss that. I mean, I have already recorded the lecture for that, so it will be online on next to next week. So I hope you will like to wait for that lecture, and then it will be more clear then, because I don't want to jump on to the again the calculation of the strain rate right now. So here we have already probably this week, 7th week, you already finished on that shock wave. So I think if I can see that, yeah, shock wave is almost finished. This is in 7th week. Then 8th week we will start with the basics of material science, and that is most of you have studied in probably your basic material science courses, and that will probably one lecture, or maybe a little bit more than one, because it's more than 1 hour. So we will probably split it into 2 or maybe 1, and then we will discuss about phase transformations that is induced during shock wave propagation. And after that we will come to this experimental techniques, how to produce dynamic deformation. So in that lecture, so we will study about this, how to calculate the strain rate. So please wait till that lecture. So I think that will be then more clear to you. There are different cases of strain rate calculation. So I got some queries, and I'm not so sure whether I have the latest queries with me. Okay, if anyone has more queries, please you can post it. Regarding the recent queries, I will post the answers in the forum very soon. So I saw that some of you have asked about the pressure discontinuity. Yeah, that's actually I feel that there was a confusion in there, and sorry about that. Probably I also did not explain it properly. So when I told that it will be multi-valued function, if you can remember this is that is when in the introduction of shock wave. So I told that pressure shock wave configuration what we have drawn, that will have a discontinuity at the shock front, and I told that it will be single valued, but that actually I will post it in today itself, that about that confusion. That exactly a discontinuity, that's not a that's vertical straight line whatever you asked about, that's not the pressure value, multiple pressure value at the same position. So that I will just post today afternoon itself. And some of you asked probably about that Wilkins-Guinan analysis of Taylor test, and then you have asked about how this the length of the plastically deformed part, that is H, is not dependent on impact velocity. So that is basically the plastic wave velocity doesn't depend on the stress directly. So the plastic wave velocity is the slope of the stress strain curve, that the plastic part of the stress strain curve. So it's not like that if the velocity will increase, the plastic, so it's not like that if the velocity increases, stresses is more, and then directly plastic velocity is also will increase in the same way, in the same order. That's not correct. So I will post the answer in the discussion forum. And then I think, if I remember you correctly, some of you asked about the relative velocity of in another question. So minus velocity is not u minus v, it should be u plus v, because it's like u minus minus v. That means suppose if a car is coming at a velocity, let's say 80 km per hour, and a car is coming from opposite direction is 100 km per hour. So the relative velocity, we generally add it, right? 80 plus 100 will be 180 km per hour. So that's the I think confusion you have. So that should be added. U plus v will be added, and yeah, probably. And some of you asked about the plastic wave as well. Sorry, the plastic wave calculation or measurement in split Hopkinson pressure bar, but that is not required now, because plastic wave generally we don't measure. We do all the calculations based on the elastic wave and whatever reading we get from the strain gauges attached to the incident bar and transmitted bar. So that will be discussed in the, as I told you, next week in the that experimental techniques chapter. So please wait till then. So I hope I can see some of you are probably watching it, and I would like to know more doubts if you have. So if some of the probably I can answer some of the doubts here, and probably we can keep some other doubts to the next lectures. If it is from the next lecture, then probably I will not discuss much here. So yeah, I think I can see only one doubt. So So as I told you, so we are now almost we finished the shock waves, and then we will discuss about that phase transformation induced during shock wave propagation, and with that we will discuss little bit of materials basics as well. So that will take a few hours, and then we will go to experimental techniques, which will not be more than 2 hours. And then what we will discuss is we will discuss about the plastic deformation at high strain rate. Basically, we will discuss the constitutive relations, the stress strain relations at high strain rate, like Johnson-Cook plasticity model, and then we will discuss about the plastic deformation in shock waves. So we will discuss about some mathematical models in that chapter as well, and after that we will have this shear strain localization or shear band formation. That will also probably take 2-3 lectures, and then we will talk about dynamic fracture. It will be little longer than probably shear band, and then if we get some time again, we can conclude the course with some applications. But what I feel is that this course will go little more than 30 hours. So I am planning for 32 to 33 hours. So we have, although I haven't recorded all the lectures, so few of the chapters are it's left. So I will try to finish as probably within 33 hours. So, and probably we will not discuss much about the applications. If we don't get time, we will stop at dynamic fracture. Dynamic fracture and shear strain localization, that is shear band, that is very important failure mechanism. Yeah. So probably there are no more queries. Okay, so I want to tell you about this. Some of you probably listed one query in that for the live interactive session, and then you are probably asking about the course materials. So as you know that so we are following the book Dynamic Behavior of Materials by Mark Mears. So this is the best book, or probably the only book available in this for this course. However, so I cannot give you a some soft copy or Xerox copy of this book, because this is not allowed, and I am using a copy from our library, IIT Guwahati library. So you can probably try to find this book, or even some of the students told me that he got a copy, I don't know, maybe a soft copy, but we cannot provide you the copy of the book. But I feel that if you follow the my slides, which are actually very concise, it will be good for, I think, good enough for your exam. And yeah, I think there are other books, as I already told, there are some other books that you can follow, but Mark Mears is a very good book. It's covered extensively on all the topics, from even experimental techniques to constitutive models, everything covered by that book. So he's a professor of University of California, San Diego, and as you can see, probably he has another book on mechanical behavior materials, Professor Mark Mears and Professor Chawla. So that is also a good book. So if you want to have some knowledge on mechanical behavior materials, which is the kind of prerequisite to this course. So you can go through that Mark Mayer's and Chawla's book. And for mechanical behavior materials, we have some other books, good books as well, like Hosport, that is also good book, and also probably Norman Dowling. So these books will tell you the basic deformation mechanisms, deformation and failure mechanisms. So mechanical behavior means actually deformation and failure mechanisms. So you can study those books. And in this course, dynamic behavioral materials, we mostly focus on the dynamic part, dynamic deformation and failure part. So it is good if you can go through some other mechanical behavior materials books, so that you can understand what happens at slow strain rate, like what happened when you were doing quasi-static test using a UTM. So although I covered little bit of material science basics in this course, so in the next week you will get the lectures on that. So that is mostly kind of it's just more than a 1 hour lecture. So I covered these things very fast, not like our usual course. So I hope you can study some of the material science basics book if you are interested more on that. So the one book is the W.D. Callister, which is a very good book, and also probably for mechanical metallurgy, for dislocations and other aspects you can use you can use probably the G. Dieter's book. So that probably we can discuss. So so I got a query from Mr. Binayaka. So, but if the velocity increases, the stress increases, and depending on the stress versus strain relation, then its slope defines the plastic wave velocity. I will actually send the answers to this question. So what is happening here is it's true, it's a little bit it's not exactly straightforward. So what happens is when you increase the stress, so suppose one material will behave in the same way. If you are taking a steel or let's say aluminum, it almost okay. So if you are taking aluminum, it will almost behave the same way if you increase the strain rate. That means it is strain rate insensitive. So if you take some other material like some kind of steel which shows significant strain rate hardening or strain rate sensitivity, then the curve will be different. And then another aspect is that if you have the curve is the same even at higher strain rate, so basically it depends on the material true stress versus true strain curve. Yes, it's actually it is difficult to generalize. So I think some suppose strain rate insensitive material. So if you increase the velocity, or the deformation will be more, but again it is difficult to tell that the plastic velocity will be higher, because when we increase the strain, the slope will decrease. The slope of the stress strain curve. So it's actually not very probably very straightforward. So and I'll post you the answer on that. So I think what the book says is the Mark Mayer's book. It's the H, that length of plastically deformed portion is independent of the impact velocity, but it depends on the initial length of the projectile or impact bar. So So what happened is that's why h by L naught is a constant. I think in the slide I saw that just yesterday the slide somewhere I made a mistake. It was, I think, I'm not so sure I modified it or not. The initial slide it says h by L equal to constant, that should be h by L naught. That I think, hope all of you understood. Sorry about the mistake. So I think yeah. Yeah, I will write the details about this, the answer in the discussion forum. I will do it today itself, by today evening. And please let me know if you have more queries, and if you have queries on some of my answers in the what I gave in the as a response of my queries, so your queries. So please let me know, because some of the answers, at least couple of questions. Okay, you are asking that one more thing, Taylor experiments does not talk regarding strain rates, but it gives its applicability with impact velocity. Yeah, Taylor test is, I think, Taylor experiment is not based on directly, he did not derive any relation with strain rate. Obviously the material behavior depends on the strain rate. So that I think highly the rate sensitive material will deform in a different way, and that the wave movement will also be different, because we know that the plastic wave velocity depends on the slope of the stress strain curve. So yeah, some of the things I think we haven't covered it, but I will write the answers to it. But this is, yeah, that is some of these tests are very early tests, are have actually a lot of assumptions in it, so not all aspects are covered. So about the materials basics, so because these things will come in the next lecture in the next week, so I just want to let you know, please ask me if you have any queries on the materials basics, because I understand that I covered that portion very fast. I mean, what I cover in my here in our BTech course in the second year, third semester BTech course, the engineering materials, we cover that portion is probably in half a semester, but I told you these things within probably 1.5 hours. So I understand that many of the things, if you are you may forget, because I'm sure that all of you did this course in your BTech second year or third year, and probably I'm not sure about your background actually. I hope that most of you are from mechanical engineering, but even civil engineering also they have some materials course in most of the colleges and even chemical engineering students learn about material science. So I think if you follow Callister's book or Z. Dieter's book or any other book, probably some of you follow the Professor Raghavan's book, Raghavan from IIT Delhi. So I hope that you can understand these things, and please ask me queries if you do not understand. And I will specifically recommend Professor Rajesh Prasad's the NPTEL lectures. So Professor Rajesh Prasad is actually one of the great teachers in material science and engineering. He was in the IIT Delhi Applied Mechanics department when I was a student, but unfortunately he did not teach us any course. But I can see that the lectures are very elaborate and very carefully explained. And if you have any issue with the understanding of suppose crystal structure or other like crystal defects, you can follow his lectures. So I just tell that regarding this materials basics, because I am very much interested to let you know that so I'll just tell you what I have covered in the materials course. Let me check it. So where I kept the materials basics, because why I am concerned, because other lectures I was like kind of, or I will be going very slow. I hope that will at least make you understand. It may not be 100%, but at least a good the most part of it. But these lectures for material science, so what I covered, I just let you know. So first I covered the classification of materials, and then which can be crystalline and amorphous, or metal, ceramic and polymer, and somehow we even classify it as ductile and brittle as well. So yeah, we talked actually I recorded this lecture, so I discussed about elastic deformation, how it look like from the atomic perspective, and then different crystal defects. So I discussed about different dimensional crystal defects, like 0-dimensional point defects, or 1-dimensional, that is called line defects, and 2-dimensional defects, 3-dimensional defects. So 1-dimensional defect, the dislocations are very important for this course. So we are generally focusing on the metallic materials in this course, not polymers or ceramics. So for metallic materials, because most of our engineering applications, especially the conventional engineering applications, so we generally use metallic materials. So that's why we are more focused on metallic materials. Metallic material means metals and alloys. And so dislocations, you try to understand at least dislocation movement. So that I have discussed what is screw dislocation, what is edge dislocation, how the dislocation moves in a crystal, and how can you see the plastic deformation after the movement of dislocations, and also different plastic deformation mechanisms. That is that one is dislocation slip, but others are like mechanical twinning, and the other one is martensitic transformation, that is phase transformation. So those are also important. Suppose for high strain rate, some materials show extensive mechanical twinning, even phase transformation. So at low strain rate, some materials may only undergo dislocation slip, that is one plastic deformation mechanism, but at higher strain rate it can go mechanical twinning or martensitic phase transformation. So those are very important topic for this course, dynamic behavior materials. And also I discussed about the different strengthening mechanism, that is again for metallic materials, and as you know, different strengthening mechanism, solid solution strengthening, strain hardening, grain boundary strengthening, precipitate strengthening, and dispersion strengthening. I think for this, if you are interested more, so you can read G. Dieter's book, that is kind of very classic book on mechanical metallurgy. I'm sure you will get some copies in your library, or yeah. So yeah, that's an important question. Till what strain rate Taylor impact test works? Yeah, I don't have the question answer right now. This is probably little difficult to answer this question. So as you know, we will discuss in the subsequent lectures. So if it is strain rate is high, the plastic deformation mechanism will be very different. So high means, as I told you earlier, just now I told you that suppose at a low strain rate it can be dislocation slip, or at higher strain rate it can be mechanical twinning or other phase transformation. But even for dislocation slip, we will discuss that in, I think, after a couple of weeks. So even for dislocation slip, the mechanism changes when you go to a very high strain rate. It's I would say that the Taylor test is probably the strain rate can be I need to check actually, but it can be probably it can go up to probably in the order of 10,000 or 10 to the power 4. So, but after that probably it will be difficult for us, I think. Yeah. Okay, dynamic yield strength which we use in Taylor series has to be described in clear. It's a bit confusing. Okay, so I will write on that. Yeah, if it is confusing probably, and all of you are probably not watching, and then I will write on that actually. So this is, there are two types of yield strength. One is kind of static yield strength. What when you do quasi-static tests, then that is we call static yield strength. But as you know, when it is the strain rate is high, probably the yield strength will be different. So what we are using in these derivations, probably the yield strength at that particular stress level. So I will actually write on that. So so that everyone can see, in the discussion forum I will write on that. So I'm sorry about that if it is, I mean, probably I did not discuss much about that. So you were saying that dynamic yield strength. Yeah, I have noted it down. So I will send you the details about that. Or if you have any other specific queries, you can let me know. So I hope, I mean, whatever we have covered till now is not very difficult for you to understand. I mean, yeah, I understand that some of the things I also probably covered, probably not in a very well explained way. But anyways, so if you are always welcome to write queries in the discussion forum. And sorry about the delay in the posting my answers. I was actually traveling probably 2-3 weeks ago, and then I could not give you the answers on time. But anyways, we will my TAs are also, they are watching it regularly, and then in future we actually want to post our answers as quickly as possible. And please understand that we have also the semester going on in here in IIT. So it's little difficult for me to and especially I have actually some part of the course is already left for recording. So that's why a little bit I am a little bit pressurized to do all before I post your answers to the queries. So I got one more query here, because as you mentioned some materials don't have strain rate variation, then it means sometimes the dynamic yield strength of the material is equal to normal ultimate strength. Yes, some of the materials probably, if it is very insensitive to strain rate, then probably yes. But what you are writing is normal ultimate strength. No, ultimate strength is different, right? I am not sure what you talked about. We are talking about the yield strength. Ultimate strength is different. That I think, hope you probably missed something, or I'm missing something. So, and probably I did not Okay, that is probably one thing I did not include in this basic material science course. So I should have included a little bit on, I think, the stress strain curve, the basic aspects of stress strain curve. I thought that all of you know about that. So we have like what is elastic limit or what is proportional limit, and how we get the Young's modulus, and what is yield strength, what is like 0.2% offset yield strength, and then what is ultimate tensile strength, or sometimes we call tensile strength, or sometimes we call ultimate strength without the word tensile, and what is flexor strength. So so these things probably we may not get time to cover in this course, so please study that. So I think the stress strain curve, and especially what is true stress, true strain, and the engineering stress, engineering strain, and the relation between true stress strain and engineering stress strain, that is very important. And you can, if you get somewhere a copy of the Horsford, I forgot his full name, the Horsford's book of mechanical behavior materials, that is good for that, and also the book on mechanical behavior materials by Norman Dowling. So there it was very nice, way it was explained that in which range you can use the true stress strain relations or definitions, and in which strain range you can use engineering stress strain relations. So so that is very well explained in Norman Dowling book, that is Norman E. Dowling, Dowling. So yeah, so I think all of these queries, some of the queries I can post it in the discussion forum, but anyways I will get these queries, when I noted it down. So I hope what you were saying is that you can probably make me clear later also. So I understood what you told, the first one, the variation. Yes, the dynamic yield strength may not be very different than, yeah. Yes, normal yield strength, yeah. Yes, I mean, yeah, that's correct actually. So if the strain rate variation is very less, probably, yeah, we can take that the initial dynamic yield strength is same, all right. So but now this is dynamic means, okay, so now coming to the point. So dynamic means actually it will be changing, okay. One thing is that the first thing is that if it is only the static yield strength, you will get a one value, and dynamic yield strength with strain with actually different higher stresses than higher than the static yield stress. So that value will change. So if you have more queries, probably you can post. Yeah, I think it is good to know that I think some of you are probably faculty. I didn't know actually your background. So I think I can see at least from your, that the Excel sheet, actually I can see that at least one or probably more of you are faculty. So it is good that you are, registering for this course. I think this course, as I probably can see that it is not available in any other probably any IITs or probably NITs. I am not sure about that. So here we are planning probably in future, even IIT Guwahati does not have this course as an elective. So I will be proposing this course as an elective, and I think this is a very important course, but little advanced. So this is probably, even if you search on Google, I think there are maybe few universities offer this course, or maybe there may be more universities which we probably cannot, probably which information is not available on the internet, but yes, yeah, the mayors don't give a detailed description, and sometimes they give brief description. Is there any other book which gives detailed description? So sorry, right now I cannot tell you any book, because I also follow mostly mayors, but there are other books. I will let you know. I am not remembering the names some of the books, but those are for different subjects. Like for maybe shock waves, you will get different book, or maybe for elastic wave you will get different book. Let's say the very basic book on, very old book on elastic wave, probably that Kolsky's book, and yeah, that's a very old book, by the way. So similarly for there are books like for impact dynamics. One book is from a professor from Hong Kong University of Science and Technology. I followed a little bit of that book as well, but I am forgetting all names now, sorry about that. So and I think for the other part, like plastic deformation at high strain rate, the constitutive model, which will become in the next week. So for those also you need to follow up some kind of book on theoretical book on where you will get all the aspects of constitutive models, that is stress strain relationship. So similarly for shock waves, probably phase transformations and other shock wave mechanisms. There are other books, so I will let you know the books, but as this is courses, as we can understand that this is for limited hours, and I thought that most of the participants will be students, and they will not spend much time on that. So yeah, for them, I think for Mark Mayer's book is good enough with whatever my slides are there. So I think please ask me any queries, because I can understand the slides are not probably it's enough for a exam purpose, but still it's probably not enough for a 100% understanding. So but if you want to learn more, I will give you some books name, and because mostly what I follow is Mark Mayer's, and with my different books and different notes what I have gone through earlier. So yeah, the only problem is, if you want to get a detailed description, so you need to have probably more than 5 books. Let's say one book for elastic wave, one book for shock wave, one book for the constitutive models, one book for let's say experimental techniques, and so these all books will be different, and even you can get for one book for applications. So but I feel that Mark Mayer's book is the kind of classic in this field, and I haven't seen any other book which covers all the aspects of dynamic behavior of materials. And so if you are more interested, and also you can probably tell me that you can write in the even discussion forum which topic you are more interested to explore more, actually, that then I can tell you some books name on that area. So but some of the old books like Kolsky's book, it probably they are good, but but new books will be probably cover more elaborately. Why this Mayer's book does not cover the details? Because it's a very big topic, dynamic behavior of materials. So it is, it's not very easy to describe all the things. Suppose this book is probably, if I am not wrong, it's more than 600 pages book. It's probably around 700 pages. So this is a subject that if you want to cover everything in details, it will be, you need to make it, probably 1500 pages or something like that. So that's the main reason. And if you want to go for, as I told you, the materials basics, so that probably you can follow the Mayer's, another book that is Mechanical Behavior Materials. He wrote the book with Professor Chawla. So you can go through that book. In fact, some of the chapters refer his Mechanical Behavior of Materials book. If you study this plastic deformation behavior at high strain rate, so that covers actually, some part of it refer his Mechanical Behavior Materials book. So, but I can understand that this course is, although we are trying even for undergraduate level, but at least good understanding of the materials basics is very much needed, especially for the part which are coming now, like from the next week. So we will discuss many things on this, suppose for dislocation movement, phase transformation, and mechanical twinning. So these are very important. And for wave, I think you can study any other book from the physics also. Sorry, I forgot the name again for this, what is it, for shock wave impact. There's a good book on the shock wave impact, and I'll let you know everything. I mean, this I will write in the discussion forum. And for constitutive models, also you need to have some basic knowledge of plasticity, some plasticity theories like Eel criteria and the hardening models. And also if you want to go a little bit more advanced, then I think what you need to do is you need to actually follow some advanced book on plasticity theory, which covers the dislocations and other details as well. So for basics of, as I told you, even Mark Mayer and Chawla's book is very good. If you want to know everything about dislocations, how the dislocations are incorporated in the models, that is constitutive models, that means the mathematical formula for predicting the stress strain behavior of a material also include these dislocation activities, like how dislocation density is changing with time or with strain. So those theories are also included in the constitutive models. So those are, we will not discuss much about it. We will discuss just very basic, because this course is, as we designed it for undergraduate students, like those students who actually know about stress strain and who know about crystals, crystal defects. I mean, I'm sure that the solid mechanics or strength of materials course or elasticity kind of course, and also basic material science course, they already covered in their first 3 years of undergraduate program. So I think a 4th year student, even a 3rd year student can understand, I think, most part of the course. So that's how we designed it, but still I understand that some of the part I did not discuss it in details, and also I understand that the Mark Mayer's book is you know, is very concise, not based on elaborate discussion. So I can see that there are no more queries. So if you think that if you don't have more queries, then we can probably stop it now, or if you have more queries, please let me know. Okay, I think Mr. Vinayaka wrote, probably what I understand is you do not have more queries. So if anyone else has some query, then we can discuss, and then otherwise we can probably probably sign out for today, and then there will be one more session, I think, on 30th September, probably the same time, 11:30 or 11 o'clock. So we can discuss more on that, and please feel free to write queries in your discussion forum. Even if I don't send the answers on time, please feel free. I mean, that is I'll be happy to answer the questions. So I think what I can understand is there are no more queries. So with that, we are signing off for today. So we'll again meet on 30th September, if I am not wrong about the date. I think it is 30th September at around the same time. So thank you.